So in this lecture, now we are learning about the mathematical formulations of the linear regressions. Okay, so before going to the mathematical formulation, just first visualize our geometrical concept. Then from geometrically we convert this concept in mathematics. Okay, so suppose this is our axis. This is we get called the independent, that is called x, and dependent axis as we called y. And let's our data set will be like this. Just I am redrawn this picture that we are drawn in previous lecture. Okay, suppose let's our data set will be like this. And you see the base fit of this line of this data is all about this line. This is the base fit line of this data, and we call this data as x1 y1 data. This data we call x2 y2 data, and this data, let's any one of this data we call x3 and y3 data. Okay, and the base fit of the plane, base fit of this data is we call it pi data, pi plane, pi line here. And this actually this point, that is the green line here, it is our x1 and it is our y1, and the predicted value of this point is this, and the predicted value will be what here, and that we call y1 hat. Similarly here predicted value will be here, and actual value is here. Here predicted value is y2 hat, and here similarly predicted value is y3 hat. Okay, here what, just see, just comes first. So if we see, now we are already discussed about the in previous lecture what will be the error. The first point we are called the error 1. Error 1 will be means our actual output minus our predicted output. This is our error 1. And in first point, what, our actual output is greater than our predicted output, so this thing will be positive in the first point. Okay, and this thing will be what, actual output means y1 y2 is actually here, and y2 minus error 2. Now let's consider the error 2. y2 minus y2 hat. This means what? This means this portion is all about our negative. Now let's see the error 3, that is our y3 minus y3 hat. y3 minus y3 math means these are both are equal. Actually the actual point and is lie on our base fitted line, so here our error will be 0. Now if you just remember the previous lecture, our base fit means what, we have to minimize all the error, summation of all the error. So if we want to minimize all the sum of the error, then here it will be positive, and you see here it will be the negative. So base fit line, just write down it. Base fit line means what, implies that minimum sum of the error. We have to minimum sum of the error, and just here you will see one error is positive and one error is negative. So if these situations happen, actually at the end of the day we have to minimize all the errors, but one error is positive and one error is negative. If we want to sum this error, then one is another is cancel out, so they are happy, they are occurred situations occur. Actually they are happy, congested situations occur, one error is cancelled out by the other errors. So it is impossible to fit the to find the minimum sum of the error. So in such situations, we have to use the square of this term, because of we have to positive everything of this error. Okay. So here, if we use the square term, then positive will be remain positive. It will okay, but negative term it will going to the positive. All the terms are going to positive if we use the square concept. So here, just using square concept here. Now, for this region, for this region, we have to square this region. Linear regressions, we call this OLS, or simply it is called ordinary least square method. Or simply it is called LSS, means linear least square. In one book is written ordinary least square, and another one is written it is a linear least square. Just don't be confused about these two terms. These both are equal. Okay. And we see that our equations of the plane, this mean what? This mean these equations is all about W and W naught. If we consider the interceptor, means this plane is, if this plane is not passing through origin, then there have two variable W and W naught. And then we have seen that these equations will be lie on like this, that is W transpose X plus W naught equals to 0. Just we have seen these equations in previous lecture, how it arises. Now, the thing is that we have to find the best W as well as W star. So we have to find W and W naught star, that is interceptor. Okay, we have to find these two terms. This one is the arc mean of between all W and W naught over all the errors. All the errors means what? Actual output of the data and predicted output of the data. And I is for 1 to n. Okay. Now just remember one thing. Here, the W, just remind it, W is nothing scalar. It is simply a vector term. And W star is what? It is just interceptor. It is a simple scalar term. Okay. And we know that our predicted value yi is coming from what? Is coming from our equations of the plane or line or hyperplane. This is mean what? This is mean x of xi W transpose xi plus x naught. Okay, our predicted value is coming for here. Now just redraw these equations. Now just rewrite these equations as simple form. Okay, just rewrite. We have to find this optimal value by using arc mean of W naught by summations I is equals to 1 to n. N means what? A number of data points in our training sets. That is yi minus W transpose xi minus plus x 0. Okay, this square. This term is the cause why we call it as linear least square method. Okay, Why it is called a least square method? Linear means what? Linear means here we are calling linear because of this. Here using linear equations here. Linear and least square we are calling because of we have to minimize these square terms. So another language it is called square laws. Okay. So because of this we are calling it as linear least square. Okay, I think till now it is clear, and this is our actual these equations is actual our mathematical optimization problem. So this is our actually this is our actually optimization problem. Now come to the regularization concept, regularizer concept. Actually we are learn about the regularizer in logistic regressions in details. What is regularizer means what? Actually regularize means to control the bias, to control the wire between bias and variance. Then here we are use the regularizer concept. So in logistic regressions, how the regularizer is useful? It is similar. If you are learn about the regularizer of logistic regression, it is as trivial according to logistic regression, as same as logistic regression. Here regularization. So okay, here we are learning the L2 regularizer. So for regularizer we are just simply regular. So don't be confused about this regularizer and regression. L2 REG means just it is I am writing here for regularizer REG, and L1 regularization, or if we using the both terms L1 and L2, it is called our elastic net. So for L1 regularizer we are calling lambda 1. L2 if we using the L1 norm, okay? If we using the L2 norm, then we call L1 regularizer, L1 norm we call L2 regularizer, and for both we call elastic net. Now let's write down the equations of it. So we have to find optimal W star as well as optimal W naught of arc mean of W and W naught over summations I is equals to 1 to n, means number of data points, yi minus W transpose xi plus W naught it whole square. This is our loss function. Okay, this is our loss, square loss. Actually it is called our square loss. As you see, these are square loss. Plus we have to add our regularizer term lambda. Just if we simple taking the L2 norm, then it is called our L2 norm, means L2 regularizer. Here we are using the L2 norm, so it is called the L2 regularizer equations. It was. So if you see the in probabilistic intuitions, so if you see this concept, I am not just discuss the probabilistic intuitions here. In this series of lecture, I am just going to discuss about the geometric intuitions of the linear regressions. So some books are using the probabilistic interpretations to finding the linear equations. If we just interested to learn about the probabilistic interpretations, then simple Google it, you can easily find it. It is not as hard as you can. It is not a rocket science merely. It is as simple. Just you can search and you can easily use. I think you can easily learn it because you are already learned the probabilistic intuitions of the logistic regressions. It is as simple as that. Okay, so I am omitting here. So simple, just remember as probabilistic interpretations here. Also here we have for linear regressions our probabilistic for a given class level of a given data set, for a class level of a given data set, means this probabilities means what? For a class level of a given data set, for a class level of a given data. This means probability in this probability, if this probability obeys the normal distributions with a mean mu and variance sigma square, then if it is obeys the normal distributions, then we are using, then in probabilistic standpoint point of view we are finding the linear regressions. Okay, in logistic regressions we are just in the last lecture you are remembering the extensions of the logistic regressions to generalized linear model. You can easily remember that if we using the multinomial distributions, then we are build the multi-class classifications. If we use the normal distributions, then we are building the linear regressions. If we use the Bernoulli distributions, then we are building the logistic regressions, and if we use the Poisson distributions, then we are using the classification regression. Counting regressions, or another language it is called Poisson regressions, that is used to predict the count. So this is our probabilistic interpretations. Probabilistic interpretation. Okay, now similarly here we are in linear regressions also. For logistic regressions, they are linear regressions. We are discussing we are already discussed. I think the geometrical intuitions and in mathematical formulations all are about clear. Now we are already discussed the geometric standpoint of view, already covered. And simple, I am just giving the hint of the probabilistic interpretations. Just simple giving the hint. Now if you are interested, then you can easily find it on Google or any mathematics class regressions. Just find any regressions books and you can easily find it. Just learn it. Now I'm not coming to cover this concept here. Now we are discussing about the loss minimizations, using loss minimization, how it is useful for linear regressions. Okay, now coming to the loss minimization concept. So loss minimization concept. Now we are coming here. Okay. Now first draw this. Okay, now we have to extend this axis. Okay, I think clear. So if you see this term square loss term, you just see this term, it is a square term, means y is equals to a square. If you just remember it, it is kind of parabola. It is a kind of parabola, and simple, if we call yi fit here equals to f of xi, and it is, if it is the loss function, so loss means what? Loss means here yi minus f of xi, that is actually error, nothing else, error square. And we see that in 0,1 loss, so our 0,1 loss will be, if it is positive, will be occurred here, and it is negative. If it is 1, then this side will be occurred here. So for binary classifications, we are already see this 0 1 loss, but here we are using the square loss, means this kind of formula. So this is a parabola, and we are already learn that equations of the parabola is like that, y equals to a square. So another language, it is called square loss. Now you see, if our data points lie on the base split plane, then error will be what? Then loss will be 0 actually. If our data points, just using another color, if our data points move positive direction, just see the graph first. If our data points, actually this point, are if move positive directions, positive directions to the fitted plane, as well as if negative direction to the fitted plane, then error, if is the square term, then error will increase positively. So if the error, if the predicted value, that is yi equals to f of x mean what? It is our predicted, this is our loss function, and this is the yi minus f of xi. If this value increases, is this error value? Actually this is what? This is means what? This means error term. If error increases positively as well as positively as well as negatively, then this square term will increases this time. So this time, okay. So because of this, it is called the error term. Now if you just remember, think we are using for classifications, what will be our loss in our classifications? Zi means what? We are just multiplications yi into f of xi. You just remember this thing for logistic regressions, and this is f of xi is mean what? W transpose xi. Here we are simply multiply these things. So this is our for classification technique, we are using this. If this is positive, then we will learn that if this is positive, then we will learn it is correctly classified, and if this is negative, then we will learn that it is incorrectly classified. Incorrectly classified. For this concept we learn in classification technique. Okay, just okay, this concept we are learned in classification technique, binary classification for logistic regressions. But here this is our error will be yi in regressions, yi minus. Here we are using the multiplications, but here we are using the subtractions. Because we are using subtraction, so for this reason we are called it here error term, linear term. This is the linear term, and this is not a linear, not a linear here, but this is a linear. So this is our actual error term. Okay, and this error we are using for our regression technique. Okay, for multiplication, for classifications purpose we are using multiplications, and for regression purpose here we are using simple subtraction for error, calculating the error. This is meant what actual or predicted yi. Okay, paralogistic regressions we call it here. And example we learn that it is also here w transpose xi into xi, here is also this equations is, that is f of xi W transpose xi plus W naught. It is a linear equations. Okay, so this is our loss minimization term. This is our loss function. Actually it is called square loss because of this, using the parabola concept. It is actually called square loss. If we for using simply square loss, we are using simple linear regression. Okay, by using simple the multiplications, we are using the classification technique, logistic regressions, and here simply using square loss functions, we are using the linear regression. So if we finalize this lecture, so loss minimization framework, if we just using the loss minimization framework for regression technique, if we just technique, then for loss minimization framework, here we are using the square loss technique to build our linear regression. Or in another language, it is called ordinary least square method or linear least square method. Okay, I think you are all about clear what is OLS and LLS, ordinary least square or linear least square, why it is called the least square. Simply because of we are here using loss functions of square loss function. So because of this, here we are calling least square method.